Have you ever looked up at the night sky and wondered where it is all going? We see a universe filled with brilliant stars, glowing galaxies and vast clouds of gas. It is a place of immense energy, light, and creation. But this vibrant cosmos will not last forever. Like everything we know, the universe has a life story, with a beginning, a middle, and an end. We are living in its glorious youth, the Stelliferous Era, the age of stars. But what happens when the last star flickers out? What does the final chapter of reality look like? This is one of the biggest questions we can ask. The universe began with the Big Bang, an incredible burst of energy that set everything in motion. First came the Primordial Era, a time of pure energy and fundamental particles before the first stars were born. Then came our time, the Stelliferous Era, where stars have forged the elements necessary for life and lit up the cosmos for billions of years. When the last star fades, a new age will begin, the Degenerate Era. The universe will become a cold, dark graveyard of stellar remnants. And when they are gone, the universe will enter its final phase, the Black Hole Era. These gravitational titans will be the last kings of a dying universe. So why are black holes the final survivors in this cosmic saga? The answer lies in their very nature. A black hole is not a thing in the way a star or a planet is. It is a region of space-time where gravity is so incredibly strong that nothing, not even light, can escape. They are born from the collapse of the most massive stars, leaving behind a point of infinite density, a singularity, cloaked by an event horizon. Because of this immense gravity, black holes are the ultimate cosmic predators. Throughout the Stelliferous and Degenerate eras, they will steadily grow. Over countless eons, they will merge with other black holes, creating even larger supermassive giants. While other objects in the universe are decaying, fading, and falling apart, black holes will be doing the opposite. They will be consolidating matter and energy. Our story starts nearly 14 billion years ago with the Big Bang. It was not an explosion in space, but rather an expansion of space itself from an unimaginably hot, dense state. In the first fractions of a second, the universe was a chaotic soup of pure energy and fundamental particles. There were no atoms, no stars, no galaxies, just a seething, expanding fireball. As the universe expanded, it also cooled. Within the first few minutes, protons and neutrons began to fuse, forming the first atomic nuclei, mostly hydrogen and helium. For the next 380,000 years, the universe remained a foggy, opaque place. Light was trapped, constantly scattering off free-flying electrons. But as the cooling continued, electrons were finally captured by the nuclei, forming the first stable atoms. The universe suddenly became transparent. This ancient light, released when the universe was just a baby, can still be seen today. We call it the cosmic microwave background radiation. But this newly transparent universe was also a dark one. For hundreds of millions of years, the universe consisted of little more than enormous drifting clouds of hydrogen and helium gas. Slowly, over millions of years, the pressure and temperature inside these collapsing knots of gas reached a critical point. A new fire was about to be lit. The first stars were about to be born, heralding the dawn of a new era. The birth of the first stars marked the beginning of our current cosmic age, the Stelliferous Era, or the Age of Stars. These first stars were unlike any that exist today. They were the cosmic forges that created the first heavy elements. These supernovas scattered elements like carbon, oxygen, and iron across space. This cycle of starbirth and death has continued for billions of years, gradually building up the chemical complexity of the universe. We are, quite literally, made of stardust. During this era, gravity continued its patient work on a grander scale. Stars gathered together to form the first galaxies, creating the vast and beautiful structures we see today. Our own Milky Way is a product of this cosmic construction, a bustling city of hundreds of billions of stars. Planets formed around stars, and on at least one of them, life emerged. The universe has been a vibrant, luminous, and ever-changing place. But this brilliant age is just a fleeting moment in the grand timeline of the universe. The creation of new stars is already slowing down. In the distant future, star formation will cease almost entirely. One by one, they will exhaust their fuel. The lights of the cosmos will slowly go out. The glorious Stelliferous Era will fade into a long, cold twilight. When the last star flickers out, the universe will enter its next phase, the Degenerate Era. This will be an age of ghosts and embers, a cosmic graveyard populated by the corpses of dead stars. The main inhabitants will be the remnants left behind by the stars of our era, white dwarfs, neutron stars, and black holes. The most common objects will be white dwarfs, the dense cores left behind by stars like our Sun. They will spend trillions of years slowly cooling down. The universe itself will look completely different. The galaxies we know today will have dissolved. Over trillions of years, gravitational interactions will slowly fling stellar remnants out of their galactic orbits. What were once majestic spiral galaxies will become diffuse, unbound clouds of dead stars, brown dwarfs, and planets drifting aimlessly through the intergalactic void. The universe will become far more sparse and empty than it is today, as cosmic expansion continues to push everything further and further apart. But even these degenerate objects are not eternal. According to some theories, the very protons that make up their matter will eventually decay. Over immense timescales, the white dwarfs and neutron stars will slowly evaporate into a bath of low-energy particles. As they vanish, they will leave behind only one type of object, the most stable and massive of all, the black holes. Black holes are the ultimate expression of gravity, and their story begins with the death of the most massive stars. When a truly massive star runs out of nuclear fuel, this cosmic balancing act comes to a catastrophic end. The outward pressure from fusion suddenly vanishes, and gravity wins decisively and spectacularly. In a fraction of a second, the star's core collapses under its own colossal weight. The collapse is so rapid and violent that it triggers a titanic explosion known as a supernova, an event so bright it can briefly outshine an entire galaxy. But the core itself continues to collapse inward, crushing matter to a density that defies imagination. The core is squeezed into an infinitely dense point with zero volume, a singularity. Around this singularity, an invisible boundary forms, known as the event horizon. This is not a physical surface you could touch, but rather the point of no return. This is the birth of a stellar mass black hole. For a black hole with the mass of a star, the event horizon might only be a few dozen kilometers across, a tiny trap for the unwary. Once born, a black hole begins a life of patient, relentless consumption. It is a cosmic predator with an inescapable gravitational lure, and its only purpose is to grow. If a star's orbit brings it too close to a black hole, it will be subjected to immense tidal forces. The stellar material is shredded and then forms an accretion disk. With each star it consumes, the black hole's mass increases and its event horizon expands. It becomes a more formidable and efficient predator. This process of growth is slow but steady. A single stellar mass black hole might take millions of years to double its mass by consuming gas and stars. But time is on its side. While the rest of the universe is winding down, fading and decaying, black holes are the only objects that are actively growing and accumulating mass. They act as the universe's ultimate sinks. Their growth is a self-reinforcing process. The more massive a black hole becomes, the stronger its gravitational pull and the larger its sphere of influence. While stellar mass black holes are fearsome, they're absolutely dwarfed by the true titans of the cosmos, supermassive black holes. You'll find them right at the very heart of almost every large galaxy. Our galaxy's central black hole, Sagittarius A, has a mass equivalent to about 4 million suns. But other galaxies harbor monsters that are billions of times the mass of our Sun. The exact origin of these giants is still a topic of intense scientific debate, but it's clear they started small and grew to their incredible size over billions of years. During the peak of their growth, these supermassive black holes became the most luminous objects in the entire universe, creating brilliant beacons known as quasars. The immense energy pouring out from the quasars could blow away gas and regulate star formation, creating a delicate feedback loop between the central black hole and the galaxy it inhabited. As the universe aged and the supply of gas dwindled, the quasars faded. The supermassive black holes settled into a quieter, more mature phase, like the one Sagittarius A is in today. The growth of black holes is not just about consuming stars and gas. One of the most dramatic ways they gain mass is by merging with each other. When two galaxies collide, Their central supermassive black holes are set on an inevitable collision course. They begin a long, slow orbital dance, spiraling closer and closer together over millions of years. This cosmic waltz is powered by the loss of energy. In the final moments of their dance, they radiate an enormous amount of energy as gravitational waves, ripples in the very fabric of space-time. The final merger is an unimaginably powerful event. The two event horizons touch and coalesce, forming a single, larger black hole. In a fraction of a second, a new, more massive titan is born. In that brief moment, the merger can radiate more energy than all the stars in the observable universe combined. The new black hole settles down, its event horizon larger and its gravitational reach wider than before. Over trillions upon trillions of years, a process of gravitational consolidation will occur. This is the ultimate destiny of matter and structure in the universe, to be swallowed and unified inside these final colossal black holes. Picture a time 100 trillion years from now. The Stelliferous Era is a distant, forgotten memory. The universe has now truly entered the black hole era. The sky is no longer a canvas of twinkling lights, but an endless, suffocating blackness. The universe has become a realm of eternal night. The temperature of the universe will have dropped to near absolute zero, just a tiny fraction of a degree above it. It's a universe that is not just dark, but also silent and still on a cosmic scale. In this future, the very concept of a place will have changed. The relentless expansion of space will have pushed everything so far apart that different regions of the universe will be causally disconnected. The universe will have fragmented into countless isolated islands of reality. Within each of these islands, a handful of black holes will be the only significant objects. For any hypothetical observer, survival would be impossible. The universe would be far too cold and empty to support any form of life as we know it. So what becomes of all the other matter in the universe? The planets, the asteroids, the dead stars like white dwarfs and neutron stars. They are the final holdouts against the all-consuming gravity of the black holes. These are the ghost galaxies, diffuse, unbound clouds of stellar corpses and frozen worlds, a faint memory of the grand structures that once existed. Over unimaginable timescales, even these resilient objects will face destruction. Gravitational interactions will continue to play out, like a slow-motion game of cosmic billiards. The planets will be the first to go. A frozen Earth might drift for trillions of years before its path intersects with the gravitational field of a wandering black hole. The white dwarfs and neutron stars will put up a better fight, but their fate is also sealed. Over eons, their orbits will decay, and they too will be consumed. This process is the universe's final slow act of cleaning up. The universe is slowly being tidied up, with all the leftover pieces being filed away into the dark archives of the black holes. While many black holes will drift alone, some will find themselves locked in gravitational partnerships. These binary black hole systems will be some of the most dynamic objects in the otherwise static universe. As they swing around each other, they constantly stir the fabric of space-time, creating faint but persistent gravitational waves. This loss of energy causes the two black holes to slowly draw closer together. Over these vast stretches of time, the dance will quicken. The black holes will spiral inwards faster and faster until they merge into a single larger black hole. On a grander scale, supermassive black holes will preside over their own complex systems. The former cores of galaxies will become enormous planetary systems, but with a supermassive black hole instead of a star at the center. Stellar mass black holes, neutron stars, and the last surviving planets will orbit the central giant in slow, majestic arcs that take billions or even trillions of years to complete. Over time, these systems will also evolve. This is the final stage of galactic cannibalism, where the central monster consumes its own children. The ultimate outcome is a slow consolidation of mass. For an almost incomprehensibly long time, the universe will consist of black holes and a sparse scattering of frozen planets and stellar corpses. But even these seemingly eternal objects may not be permanent. If this is true, then matter itself is destined to dissolve. Over these immense timescales, one by one, their constituent particles would spontaneously decay into a puff of lighter particles. This would be an incredibly slow evaporation. A single stellar remnant would take an unimaginable amount of time to completely vanish. dissolving into a faint mist of low-energy radiation. The consequences of this are profound. It means that all the matter forged in the hearts of stars is transient. Nothing made of normal matter is forever. As the last white dwarf evaporates, the Degenerate Era truly gives way to the black hole era. Now there is nothing left but the black holes themselves, the sole keepers of the matter and energy that once made up the vibrant cosmos. They're like cosmic time capsules, holding the story of their vanished galaxies within their event horizons. But even their reign is not eternal. For a long time, black holes were thought to be truly eternal prisons. But in 1974, the physicist Stephen Hawking made a revolutionary discovery that changed everything. By combining the laws of general relativity with the strange rules of quantum mechanics, he showed that black holes are not completely black after all. He predicted that they must slowly leak energy back into the universe. Hawking's idea is rooted in the bizarre nature of empty space at the quantum level. What we perceive as a perfect vacuum is actually a bubbling, fizzing sea of virtual particles. Hawking realized that if one of these particle pairs appears right at the edge of a black hole's event horizon, something remarkable can happen. It is possible for one particle to fall into the black hole, while its partner escapes into space. The particle that escapes becomes a real particle, carrying energy away from the black hole. This negative energy is subtracted from the black hole's total mass. The net result is that the black hole loses an infinitesimal amount of mass. This process is astonishingly weak. For a black hole with the mass of our sun, the temperature of this radiation would be just a tiny fraction of a degree above absolute zero. The evaporation of a black hole is a process of almost unimaginable slowness. Paradoxically, smaller black holes are hotter and evaporate faster than larger ones. A stellar mass black hole would take around 10 to the power of 67 years to completely disappear. That is a timescale so vast that if you were to count every atom in the observable universe, you would not even come close to this number. The supermassive black holes will take far longer still. The largest among them could persist for a googol years, or 10 to the power of 100 years. For the vast majority of its life, a black hole's evaporation will be a quiet, steady, and unremarkable affair. For eons upon eons, it will be a near perfectly stable object. But as a black hole nears the end of its life, the process accelerates dramatically. As its mass dwindles, its temperature skyrockets, and it begins to radiate energy at an ever-increasing rate. In its final moments, all the remaining mass is converted into energy in a final, brilliant flash of light. The death of a supermassive black hole would be the most spectacular event to happen in the universe for a googol years. After the last black hole has evaporated, the universe will enter its final, ultimate state. This is the Dark Era, a future so empty and desolate it almost defies description. The universe will have reached a state of maximum entropy, a condition often referred to as the heat death. In this state, there is no more potential for anything to happen. There are no temperature differences to drive any processes, no gravitational gradients to pull things together, and no complex structures left to evolve. It's the ultimate equilibrium, a state of perfect and final rest. The cosmic story, which began with the fiery brilliance of the Big Bang, will have concluded in a cold, silent whimper. The arrow of time itself may lose its meaning, as there is no longer any change to mark its passage. This future raises some truly profound philosophical questions. What happens to the information that made up the universe? This is the famous black hole information paradox, a deep puzzle at the heart of modern physics. As we contemplate this final state, we are left with a sense of awe and humility. We are living in a fleeting, brilliant moment of cosmic history, a brief flicker of light and complexity between two eternities of darkness. We have traveled on an extraordinary journey across the entire lifespan of our universe. We started in the fiery cradle of the Big Bang, witnessed the birth of stars and galaxies, and watched as they faded into a long, cold twilight. Here in this realm of eternal night, black holes stand as the last titans, the final keepers of cosmic history. They are the ultimate monuments to everything that has ever existed. The story of black holes teaches us a profound lesson about time and permanence. In our everyday lives, we think of mountains and monuments as symbols of eternity, but on a cosmic scale, they are as fleeting as a whisper. The legacy of black holes is therefore a dual one. They are agents of destruction, swallowing matter and erasing structure, but they are also the universe's ultimate archivists. As we stand here today, we can look at black holes not as terrifying voids, but as cosmic laboratories. They push the laws of physics to their absolute limits, forcing us to confront the deep connections between gravity, quantum mechanics, space, and time. By studying them, we are not just learning about the end of the universe, we are learning about its fundamental operating system. The black hole is the final character in the cosmic story, but its legacy begins now, in our quest to understand it. Contemplating the end of the universe can feel daunting, even bleak. But I believe there is another way to see it. This grand cosmic story gives us a profound sense of perspective. We are living in a special, fleeting moment, a brief, brilliant era when the universe is alive with light, complexity, and the potential for discovery. Knowing that it will not last forever makes this moment all the more precious. Our ability to even ask these questions is a testament to the remarkable power of the human mind. Through science and curiosity, we have pieced together the story of the entire cosmos. We are the universe's way of knowing itself. The story of the black hole era is not just a scientific forecast, it is an invitation to wonder. It inspires us to continue our quest for knowledge, to build better telescopes, to devise new theories, and to keep pushing the boundaries of what we know. Ultimately, the tale of the universe's end is a story of transformation. Matter becomes energy, stars become black holes, and black holes become radiation. It is a story of cycles on the grandest possible scale. The universe is the most magnificent story ever told, and we are incredibly fortunate to be here right now to read a few of its pages. The adventure of discovery is far from over.